Okay, today let us discuss about momentum equation, expression for velocity of sound wave in fluid, velocity of sound wave in terms of bulk modulus that is represented by K, and velocity of sound for two important cases. First one is isothermal process where temperature remains constant, and velocity of sound for adiabatic process, that is there is no heat transfer, Q equal to 0, there is no heat transfer from outside to inside or inside to outside, or you can tell like there is no heat transfer from system to surrounding or surrounding to system. So let us go for momentum equation. You already studied about momentum in second PU as well as in elements of civil engineering. The momentum is given by mass into velocity. So here is the momentum per second of a flowing fluid. This is applicable for fluid case. So momentum of per second of a flowing fluid, or that is called as momentum flux, is equal to, as this is a momentum per second, I have to consider mass per second here, is equal to product of mass per second, that is represented by a m dot, and velocity of the flow, that is v. So mathematically the momentum per second of a flowing fluid that is applicable for compressible or incompressible is given by, that is equal to rho av into v, where rho av is, I already discussed about this thing in Cartesian continuity equation, Cartesian coordinate. So rho av equal to m dot and into v. So rho av into v, that is a momentum per second. So where rho av equal to mass per second, that is represented by m dot. Now the momentum equation for compressible fluid for any direction may be expressed as net force in the direction of s, that is any direction, equal to rate of change of momentum in the direction of s. So that is equal to, I already told, mass per second. Here the rate of change of momentum. So rate of change of momentum means you have to consider change of momentum here. So mass per second, mass remains constant. You cannot apply change here. But only the modification you can make here is in velocity. So change of velocity, mass per second into change of velocity, mass per second is rho av, and change of velocity is final velocity minus initial velocity, that is v2 minus v1, where v2 equal to final velocity in the direction of s and v1 equal to initial velocity in the direction of s. So equation is rho av into v2 minus v1. You have to remember this thing. This is needed for solving or deriving the expression for velocity of sound. Now expression for velocity of sound wave in a fluid. So you can take into consideration of throwing any object or stone into water because of the disturbance, that is throwing water into throwing object or stone into the water, that is the means of creating disturbance. Because of the disturbance, water waves moves. You can see the wave formation in water. So similar context you can apply for this also. So this is a expression for velocity of sound wave in a fluid. So disturbance creates pressure waves in a fluid. So because of the disturbance, you'll have wave formation here. So these pressure waves travel with the velocity of sound wave in all directions. So these disturbances are going to move in all directions as in 3 dimension. But for the sake of simplicity, you can assume one dimensional case here. So the experimental setup consists of a right long pipe of uniform cross-sectional area, that is A, fitted with a piston. This is a simple piston cylinder arrangement. Let the pipe is filled with compressible fluid which is at rest initially. The fluid is at rest, that is it is not going to move initially. The piston is moved towards right and a disturbance is created in the fluid. So because of the piston movement, you are going to create a disturbance in the fluid. This disturbance in the form of pressure wave which travels in the fluid with the velocity of sound wave, that is going to move with the velocity of sound wave. So this is the experimental setup here. So it consists of piston cylinder arrangement. Area of cross section of the piston is A. You can see there. You are going to make you are going to give a piston a moment of or displacement of x. Because of that, the pressure waves are going to move by a distance L. You can see the wave front there. So let us define the terms. Let A equal to cross-sectional area of the pipe, V equal to velocity of the piston with which the piston is going to move, P equal to pressure of the fluid in the pipe before the moment of the piston, there is an initial pressure at rest, rho equal to density of the fluid before the moment of the piston, there is an initial density, dt equal to a small interval of time with which the piston is moved. This is a small time during which the piston is going to move. So C equal to velocity of pressure wave or sound wave traveling in the fluid, or velocity of the disturbance. So now from basic definition of velocity is given by distance by time. Now you have to calculate distance here for piston as well as for the sound wave. So distance equal to V into time, velocity into time. So distance traveled by the piston in time, we are going to give piston a displacement of x. So distance is x. X equal to velocity is v. We are going to move the piston with the velocity v, and time interval is dt. So x equal to v into dt. Similarly, distance traveled by the pressure wave in time dt. So there is a disturbance that is going to move with it is going to move a distance of L. So L equal to velocity of the pressure wave. I already told velocity of the pressure wave is taken as capital letter C. So C into time, time is small interval dt. So C into dt. So L equal to C into dt for pressure wave, and x equal to V into dt for piston. Now, as the value of C will be very large, hence C into dt will be more than V into dt, because pressure waves has a velocity more than compared to the velocity of the piston. So product C into dt will be more than product V into dt. For the time interval dt, the pressure wave has traveled a distance L and piston has moved through x. You can see the diagram here. When you are going to move a piston by a distance x, the pressure waves are going to move a distance L, L equal to C dt. L into C dt. Therefore, the fluid in the length of the tube equal to L minus x, the fluid will be compressed, because when you are going to give a piston a displacement of x, the remaining region, that is L minus x, the fluid will be in compressed state. Due to the compression of the fluid, the pressure and density of the fluid will change. The pressure as well as density from equation of state PV equal to mRT. When the pressure increases, density increases as well as the temperature increases. So let us define the terms. P plus dP, that is equal to pressure after compression. Initial pressure is P, then there, because of the compression you will have increase in pressure, so that is you have to add that pressure to initial pressure. So P plus dP. Similarly, rho plus dP, initial or density plus change in density after compression. So rho plus d rho equal to density after compression or density of the fluid in the length L minus x. In the length L minus x, the fluid will be in compressed state. So now mass of the fluid for a length L before compression, because we are going to apply here continuity equation, mass before compression equal to mass after compression, because mass is going to, it is not going to change because of the compression, only density and pressure and temperature that is going to change. So there is no variation with respect to mass, so mass remains same according to continuity equation. So let us just calculate mass before compression for a fluid for a length L before compression, that is equal to, so from basic definition of density, density equal to mass by volume. So mass equal to density into volume. So density is rho, volume of the fluid is given by area into length. So as a unit of area is meter square and unit of length is meter. So meter square into meter, that gives meter cube. So rho into volume of the fluid up to length L. So that equation becomes equal to rho into AAL, rho into AAL, rho into A into L, that is equal to, you have expression for L equal to C dt. So rho A into C into dt, that as rho L equal to C into dt, as it is a distance traveled by pressure wave. So from take it as equation 1. Now mass of the fluid after compression for a length L minus x, again this is because L minus x region you are going to consider just because the fluid will be in compressed state in L minus x region. So that is equal to density of compression into area into length. It remains, equation remains same, but you have to modify here. In place of density, rho plus d rho, and area remains constant into a cross sectional area. Now length instead of L, you have to consider L minus x. So overall expression becomes rho plus d rho into A. In place of L, you can substitute C dt, that is from actually distance traveled by sound wave. In place of x, you can substitute V dt, that is the distance traveled by piston. So C dt minus V dt, as L equal to C dt, x equal to V dt. Take it as expression 2. Now from continuity equation we have mass of the fluid before compression equal to mass of the fluid after compression. So equation 1 and 2 you can club together here, combine together. Rho into A into C into dt equal to rho plus d rho into A into C dt minus V dt, or you can take a dt common from your right hand side equation. Rho into A into C into dt equal to rho plus d rho into A into dt into C minus V. So dividing entire expression by A dt, we get rho into C, as you can cancel A dt from left hand side equation. rho into c equal to rho plus d rho into c minus v. You can multiply c minus v inside rho plus d rho. So that becomes equal to rho c minus rho v plus c d rho minus v d rho. So therefore you can just make the rearrangement c d rho equal to rho c minus rho c plus rho v plus v d rho. You can cancel rho c term here. So remaining terms are equal to rho v plus v d rho. I will take it as expression 3. But the velocity of the piston V is very small as compared to velocity of the pressure wave C. I already discussed about this thing. Also the value of d rho is very small. Can you guess the reason for this? This is just because change in density is very small compared to initial density. So d rho is very small, and again V is very small compared to velocity of sound wave or disturbance. Hence the overall term V into d rho will be very small, because multiplying small quantities, that gives again smaller quantity. So V into d rho will be very small and can be neglected. Hence equation 3 becomes equation 3, you can see there c d rho equal to rho v plus v d rho. You can neglect v d rho term. So modification of equation 3 is equation 4, that is c d rho equal to rho v. Now when the piston is moved with the velocity v for a small time interval dt, the fluid which is at rest initially will move with the velocity equal to velocity of the piston. The meaning of this sentence is, when you are going to move the piston with the velocity v, the fluid whatever that is there inside the pipe, that is also going to move with the velocity of piston. So also the pressure of the fluid will increase from P plus dP due to the movement of the piston. Because of the compression, there will be increase in pressure. Initial pressure is P. Now final pressure becomes P plus dP. Now hence applying the impulse momentum equation, we get to remember this thing. Impulse momentum equation is given by net force on the fluid, that is equal to rate of change of momentum. Now net force, from where you are going to get this net force? Net force acting on the fluid is pressure force. Initial pressure is P. So pressure is given by force by area. So from force equal to pressure into area. So initial pressure is PA, pressure force is PA, and final pressure force is P plus dP into A, as the area of cross section remains constant. So net force on the fluid, the net force it is acting on the fluid, that is given by final minus initial. So final pressure force is P plus dP into A minus PA, that is equal to mass per second into change of velocity of the fluid, that is from momentum, rate of change of momentum per second. So dP into A, so mass per second is mass divided by time into change of velocity of the fluid. You have to remember here it's a change of velocity of the fluid, not velocity of sound wave. So velocity of sound mass per second, that is total mass divided by time into V minus 0. 0 just because here the velocity of the fluid at rest or initial velocity is 0, and final velocity that is equal to velocity of the piston, that is given by capital V. So mass is given by rho into A into L, that is from equation density equal to mass by volume, mass equal to density into volume. So volume is area into length. So rho into AL divided by time interval is dt into V minus 0. But in place of L, you can substitute c dt, that is from distance traveled by sound wave. So rho A c dt divided by dt into V minus 0. Now you can cancel dt terms here. So remaining expression is rho A c into V minus 0. That is equal to rho A c V. Or you can get expression for dp here. dp equal to rho A CV divided by A. So you can you can cancel A terms here. Rho A CV divided by A, that becomes rho CV. So now you can get expression for C equal to dP by rho V. Take it as expression 5 upon rearrangement. Now multiplying equation 4 and 5 we get. This equation 4 is C d rho equal to rho v, and equation 5 is C equal to dP divided by rho v. So you can just multiply right hand side to right hand side, left hand side to left hand side. So C square d rho, that is equal to rho v into dP by rho v equal to dP. That is just because you can cancel rho v terms there in right hand side equation. So C square d rho equal to dP. Now C square equal to dP by d rho upon rearrangement. Now you can take, actually C is the velocity of sound. You want expression for velocity of sound. Therefore C equal to, by taking square root, C equal to square root of dP by d rho. Take it as equation 6. Now this is the expression for velocity of sound. that is equal to the square root of rate of change of pressure to the change of change of density of the fluid due to disturbance. Rate of change of pressure in the sense that is dp, rate of change of density means that is d rho. So it is given by c equal to square root of dp by d rho. That's the equation 6. Just remember this equation. Now we have to derive velocity of sound in terms of bulk modulus, that is k. Hope you remember a definition of bulk modulus from properties of fluid from first module. So bulk modulus k is defined as k equal to increase in pressure divided by volumetric strain. Volumetric strain is given by change in volume divided by original volume. So here decrease in volume divided by original volume. So equal to dp divided by minus dv divided by v, where dv is decrease in volume. I'll explain about this thing later. V equal to original volume. So negative sign, you can ask question here why we are going to consider negative sign here. So here, as you all know, pressure increases because of the moment of the piston. As pressure increases, from equation of state PV equal to mRT, volume increases. P is inversely proportional to V. So or P equal to 1 by V. So because of that, there is an increase of pressure, there is a decrease in volume. So you have to consider negative sign here. Now we know mass of the fluid is constant. That is, mass is given by, this is not mass per second. Mass per second is rho av. Here it is just mass, that is in kg. So rho into volume, that is from density equal to mass by volume. Mass equal to density into volume. So that is equal to constant. Since mass equal to rho into volume, or rho v equal to constant because volume is represented by v. So differentiating above equation, treating rho and v as variables. So apply product rule, considering rho as first term and v as second term. So rho into dv plus v into d rho equal to 0. Just take vd rho to the other side. Rho dv equal to minus vd rho. So dv divided by v equal to minus dv by v equal to d rho divided by rho. Substituting the value of minus dv by v in equation 4. The equation 4 is, okay, you can substitute in equation 4. There's a k, you take it as k as equation 4. We are going to get k equal to dp divided by d rho divided by rho. You can take rho to the numerator, rho into dp by d rho, or dp by d rho equal to k by rho. K is a bulk modulus, rho is density. Now you can substitute back this dp by d rho equal to k by rho in equation 6, that is c equal to square root of dp by d rho. So in place of dp by d rho, you can substitute k by rho. So that becomes, equation becomes c equal to square root of dp by d rho equal to square root of k by rho. So equation 7 gives velocity of sound wave in terms of bulk modulus and density. So k is a bulk modulus and rho is the density. This equation is applicable for liquids as well as gases. Okay, now let us apply this velocity of sound concept for two important processes, isothermal process and as well as adiabatic process. So isothermal process where temperature remains constant. So it is given by P by rho equal to constant. So now you can take rho to the numerator. So P into rho to the power minus 1 equal to constant. Again, it is similar to deriving expression of velocity of sound in terms of bulk modulus. Just consider P and rho as variables and just apply product rule. Considering P as first term, rho to the power minus 1 as second term. So P into minus 1 into rho to the power minus 2 into d rho plus rho to the power minus 1 into dp equal to 0. So dividing entire expression divided by rho to the power minus 1, we get minus 1 into p, that becomes minus p. Rho to the power minus 2 divided by rho to the power minus 1, you can cancel rho to the power minus 1 over there. Minus p into rho to the power minus 1 into d rho plus dp equal to 0. Now upon rearrangement, you can take rho to the power minus 1 again to the denominator. So minus p divided by rho into d rho plus dp equal to 0. Now you want expression for dp by d rho, so that can be obtained as like this: dp equal to p by rho into d rho, or upon rearrangement dp by d rho equal to p by rho. Now from equation of state, p by rho equal to RT. So where is R is a gas constant, T is the absolute temperature. Substituting the value of this dp by d rho in C, that is expression 6, we get C equal to square root of dp by d rho, that is equal to RT or p by rho. So this is the expression for velocity of sound for isothermal process. Now last one, velocity of sound for adiabatic process. So you have to remember this expression. Adiabatic process means where there is no heat transfer from system to surrounding or surrounding to system, or Q equal to 0. So adiabatic process is given by P divided by rho to the power gamma equal to constant, where gamma is ratio of specific heat, that is given by Cp by Cv, and P is the pressure, rho is the density, that is equal to constant. Again, similar to isothermal process, you can take rho to the power gamma to numerator. That time it becomes rho to the power minus gamma. So P into rho to the power minus gamma equal to constant. Differentiating above equation, considering P and rho to the power minus gamma as variables, and applying product rule, considering P as first term and rho to the power minus gamma as second term. So P into minus gamma into rho to the power minus gamma minus 1 into d rho plus rho to the power minus gamma into dp equal to 0. Similar to isothermal equation, to divide by rho to the power minus gamma, we get minus P into gamma rho to the power minus gamma minus 1 divided by rho to the power minus gamma, that becomes rho to the power minus 1 into d rho plus dp equal to 0, or dp equal to, you can take to the other side, minus becomes plus here, dp equal to gamma into p divided by rho into d rho, or you have to get expression for dp by d rho. Dp by d rho equal to p by rho into gamma. So P by rho from equation of state, we have value as RT. There's R is a gas constant, T is the absolute temperature in Kelvin. So in place of P by rho, you can substitute RT gamma, or that is equal to gamma RT. In place of gamma, you can consider in R.K. Bansal textbook, they have considered K value. In place of gamma, they have considered K. So you can use any symbol, gamma or K. So that is equal to gamma RT. Now substituting the value of dp by d rho in equation 6, that is C equal to square root of dp by d rho. So that time it becomes C equal to square root of dp by d rho equal to p by rho, that is equal to gamma RT. So because p by rho equal to RT, C equal to square root of dp by d rho, sorry, in place of Cp by d rho, you can consider you can substitute gamma RT. So you are going to get C equal to square root of gamma RT. Note, you have to consider these two important points. For the propagation of minor disturbances through A, the process is assumed to be adiabatic. Because there is no heat transfer. The velocity of the disturbances or pressure waves, otherwise it is called as pressure waves, through air is very high. Hence, there is no time for any appreciable heat transfer. That's what I explained. There is no heat transfer. So isothermal process is considered for the calculation of velocity of sound waves or pressure waves or disturbances only when it is given in the problem that the process is isothermal. If no process is mentioned, it is assumed to be adiabatic. This is important point for solving the problem. If they are going to specify it as it has some isothermal, then you have to consider isothermal. Otherwise, it is considered as adiabatic process. So this is about velocity of sound wave. This is very important question. Every year they are going to ask this question for 10 marks. This is a short question from 5th module. So you can study this expression. You can write down in your notes. From tomorrow's video, I'm going to explain about problem solving and Mach number, Mach cone and all. Okay, thank you.